Today, we want to talk a little bit about the divergence of a vector field. This is from the divergence theorem, where we measure the divergence of a vector field at every point in a solid W. And this is equal to the flow of that vector field through the surface of the solid W. This is that fundamental theorem of calculus thing, where we integrate a derivative by evaluating the function at the endpoints. In this case, the divergence being some kind of derivative of the vector field, and we evaluate the vector field at the surface of the solid. In this case, that vector field dot dA, the flow of the vector field through the surface. So we calculate the divergence of the vector field at every point in a solid, and that's just calculating the flow of the vector field through the surface of the solid. So we want to think about what this divergence means. We know a little bit more about surface integrals. One of the ways that we interpreted the flow of a vector field through a surface is we imagine the vector field to be the flow of a liquid or some kind of the flow of air or water, and then S is some surface. How much? And this flux integral will tell us how much water or air or whatever is flowing through the surface. So the divergence theory going the other way, what would be? We can just look at what the divergence is of the vector field at every point inside the solid. All right, so let's talk about the divergence. We're going to start talking about divergence by thinking about sources and sinks. We're going to imagine a point being a source and a sink. And when we talk about a point that's a source, that means our vector field is flowing away from that point. I gotta be careful drawing my source point this way. Some of you might play 40K. Start thinking blood for the blood god, but that's not what we're worried about. What's happening is at this vector field, this point, when we think of a point as a source, we're thinking of the vector field moving away from that point. So this is the center of an explosion. A sink would just be going the other direction. The vector field would be flowing towards the point. So what we're going to want to try to measure is how much boom is going on at the point, or how much reverse boom, how much move is going on at a point. Is it drawing stuff in, or is it pushing stuff out? We can see that a source is just -1 times a sink, because we just changed the direction of the vectors. So if we stand way back from the divergence theorem, what we're going to be measuring is how much, if we have a point that is a source, for example, inside of a small sphere, and there's a lot of boom going on, then we're going to have a lot of flow through the surface of that sphere. Or if we have a point that's a sink, then it's going to be the vectors are going to be pointing in towards that point. Then at that point, we'll be measuring how much of the vector field is flowing through the surface near that point. Then we're just going to do our other calculus thing. Instead of looking at a small sphere, we shrink that sphere down to a point. We shrink that solid down to a point. So this has all the trappings of a regular calculus thing. Its fundamental theorem of calculus means we're going to be integrating a derivative by looking at the function at the boundary. And here we're going to imagine the divergence, a source point. We're going to imagine how much flow is going through a surface of a small sphere around that point. And then shrink that point, shrink that sphere down to a point. We get a better approximation by doing something more often. So we just do things infinitely often. We shrink little spheres all the way down to points. Any questions about how this is a calculus thing? We want to see the structure in the fundamental theorem of calculus, and we want to see the calculus thinking. Just do the thing an infinite number of times. Those are the two main lines in calculus. When in doubt in calculus, figure out how doing the thing more often will help, or think about a fundamental theorem of calculus. Unless you're taking a math test, in which case take the derivative, set it equal to 0, and solve. I haven't looked at an AP calculus test for a while, mostly because I don't need to, but it used to be that if you wanted to pass the AP calculus test, that is get a 3, all you had to do was take the derivative, set it equal to 0, and solve. And that would give you a sufficient number of points to just pass. It becomes a really tricky thing. Because if I say find the derivative of this function, or I have to ask a question that just involves finding the derivative of the function. If you find the derivative of the function, then set it equal to 0 and solve. You've done extra stuff. I said find the derivative, and first step was you found the derivative. Should you mark off points for going too far? Because at a certain point, someone said, well, I found the derivative. But the question becomes, why didn't you know that that was the end of the problem? Why did you do this extra stuff? Were you showing off? You know what I mean? It's an indication that you don't really know what you're doing. Yes, you found the derivative. That was one step. But you thought that was one step of a larger problem. And this is not that large a problem. You know what I mean? What would you do if that happened to you? I just said find the derivative, and then you did a bunch of extra steps, and you lost points for doing extra steps. Are you in a defensible position? I know what a lot of students would do. They would erase the stuff that they wrote and try to pretend like they didn't write it, as if you can't see it sitting there all erased on the paper. Like, well, this is not like a Word document where you just delete a section and there's no evidence that it was there. I mean, it's a piece of paper. You damaged it by writing on it, and you damaged it some more by erasing on it. It's not like it's going to be invisible. You know what I mean? What are we talking about? Oh, yes. So let's take a look at more of the detail. That's our idea. Imagine how much of the vector field is flowing through the surface. Now, this is just at a single point where we have a source or a sink flowing out or flowing in. That's going to be the orientation that we had in line integrals and surface integrals. We have two orientations, flowing out and flowing in. what is it, -1 times the other. Let's talk about what the divergence of a vector field is. So the divergence, if F is a vector field with F1, F2, and F3, write that down. Where F1, F2, and F3 are the components of the vector field F, then the divergence is just the partial at F1 with respect to X, plus the partial at F2 with respect to Y, plus the partial at F3 with respect to Z. This is the result of performing an operation on the vector field F. And we have a name for this operator. So this is the divergence of F is a dot product of del dot F. So it's an upside down triangle. Right side up triangle, we would call it a delta. When we flip it over, we call it the del operator. The del operator is just the partial with respect to xi. It's a vector. It's the partial with respect to xi plus the partial with respect to yj plus the partial with respect to zk. So del operator is a vector but instead of multiplying, we perform this operation. So when we find the dot product, a del dot f, we have the partial with respect to x of f1 plus the partial with respect to y, f2 plus the partial of f3 with respect to z. So this del operator is a vector. And the dot product, this del operator, and a vector field is the divergence of that vector field. We have seen the del operator before. We haven't, this is the first time we've applied it to a vector field, but we've seen the del operator before. The del operator shows up when we were talking about gradient. The gradient of a function is the del operator applied to that function. That's why we see the gradient of f is del f. In this case, we're just applying the del operator to a function of three variables. And we're getting a vector field. Here in the divergence, we're taking the del operator dot the vector field, and that's why we're getting this scalar, the divergence. But if we have the partial with respect to xi, plus the partial with respect to yj, plus the partial with respect to zk, if we apply this operator to a function of three variables, we just apply the partial with respect to x to the function for the I component, the partial with respect to y to the function for the j component, and apply the partial with respect to z to the function for the k component. And that's how we built the gradient. So the gradient of f is del f. The divergence of a vector field is del dot the vector field. And so we're taking this del operator and thinking of it kind of in terms of a scalar multiplication, then a dot product, which means one more, and that would be the cross product. So we take this del operator, which is a vector, and we can apply it to a scalar function of three variables. That gives us the gradient result. So we apply the del operator to a scalar function, we end up with a vector, and that would be the gradient vector. We take the del operator and form the dot product with the vector field, and we get the divergence of a vector field. This is giving us, in a sense, how much the vector field is blowing up at a point. Telling us what direction things are going at that point, or how fast things are going at that point. Because when we think of derivative, if we're thinking of our vector field as the flow of water or air, then our vector field is a speed, and our divergence is going to be some kind of acceleration. The vector curl is the cross product of the del operator and the vector field. So if we take the cross product, we'll find the determinant of ijk, then the del operator, and then the last row, we put the function, the vector field f. In this case, we calculate the same way we normally do. The I component, we would just take out that row and column containing I, and then make the determinant of this 2 by 2 matrix. Instead of multiplying the d dy times f3, we're thinking of applying the d dy operation to f3. So we'll start off with the partial with respect to f3. So the partial of f3 with respect to y minus the partial at f2 with respect to z. If we remember where the curl comes from, this is just the first term. We're going to find other terms. If we remember where the curl comes from, the vector curl comes from in this cross product, and we remember how we calculate cross product, that will help us remember what the vector curl should look like. So notice that I, which has to do with the partial with respect to x and f1, we're calculating the determinant without that stuff. There's no partial with respect to x. There's no f1. Also, since the way we calculate determinants is to go a d minus bc, I'm never going to have a partial with this of f2 with respect to y. I'm never going to have any matching ones from the same column. Partial at f3 with respect to y minus partial at f2 with respect to z. Nothing matches up. And neither of those, f2 and f3, are not that first column. And partial with respect to y and partial with respect to z are not that first column. So that informs us how the rest of the terms are going to show up. J is going to involve f1 and f3, and the partial with respect to x and the partial with respect to z. But we don't match them up. I don't do partial of f1 with respect to x. It crosses up. Partial with respect to x gets applied to f3. So I'm going to have the partial at f3 with respect to x minus the partial at f1 with respect to z. Because we're calculating a determinant with cofactor expansion along the first row, we have to start positive, but then the next term is negative because determinants alternate. The next one will be positive. It's going to be the coefficient of k, so it's going to involve f1 and f2, partial with respect to x and partial with respect to y. They never match up. So I have the partial at f2 with respect to x minus the partial at f1 with respect to y. This is the way that I prefer to remember, with the j term being negative, because I like to remember this using this cross product, rather than just trying to take this expression and remember it. You can remember this expression by remembering where it came from and understanding how determinants are calculated. But a lot of times you might see this middle term written with a positive, and then the terms reverse. So multiply by -1, and you might see plus partial at f1 with respect to z minus the partial at f3 with respect to x as the coefficient of j. I can't say for certain why it bothers me so much, but it's like 3, 2, 3, 1, 2, 1. It's always kind of descending to get the signs right. And then if you distribute the negative just because to make the term positive, then it's like 3, 2, 1, 3, and then 2, 1. I don't know why that makes me so mad. It doesn't make any sense at all, but it does. Maybe that should be my whole final exam. It's just multiple choice. And I just put like stuff like this where these two are in place. I go, which one does Leach prefer? And I go, oh, I know he doesn't like this plus j thing. So it's clearly this one, even though they're exactly the same thing. You know what I mean? Then you might be thinking, dude, a math test shouldn't be about the teacher's personal preferences about how things are written. And I would suggest that every math test already is just a personal expression by your instructor. They picked the problems, they told you how to answer them. And you kind of have to play their game so that you can get points and move on to the next class. You know what I mean? So I never get more very far in Skyrim, because at a certain point you have to make a choice. You either go with these guys or go with the other guys. And I go, I don't want to do either of these. And so I just stop. And I go, man, he said he was gonna go kill that dude. Have you heard if he's dead or not? No, I've heard he's been out there doing other stuff. But no, I didn't. Well, I'm sure he'll do it. You know what I mean? One of those things, we like to think math is like all purely objective. It's just objective. And then you look at how we apply math to society, and it's like, oh, wow, this is kind of super racist, what we're doing here. You know what I mean? Math is racist. We'd like to think of it as being this universal thing. But once we start communicating and we figure out what each other's numbers mean, then the rest of it is arcane symbols. That's going to be hard to figure out. Are there cultures out there that don't think of vectors in this way? And I don't know, because I was brought up in American schools. And so I'm only ever going to have this one viewpoint. I suppose I could go out and get other viewpoints, but I think I'm too old to do that. Is that? No, I don't think I can. Yeah, that's why. The start all over again part. I can't remember the exact moment where I absolutely 100% would not be going back for a PhD. I don't remember the exact moment. But I know that there was a time where I was like, oh, I think I want to get a PhD. And that has morphed over time into me looking at PhD and saying, well, I am absolutely 100% not going to be doing that. You know what I mean? Which is why it's really hard to listen to me. And you should be very suspicious when I say things like, you shouldn't get a PhD because some outside force is telling you to get a PhD. In my view, the only reason that you should get a PhD is because you have to get a PhD. You, and only you, decided that you have to get a PhD. Does that make sense? That's the level of commitment that I want from everybody that's going to pursue a PhD. If you're just going to do it because your parents said you had to do it, you've got to get your PhD. Or, I don't know, whatever. They threaten you with something. That's not how PhDs work. Like if your parents is like, oh, you are definitely going to get your bachelor's degree. You are graduating from college. Okay, you can get through a bachelor's degree just by force. Someone could just like force you to get a bachelor's degree. You're all right, suck it up and do it. But if that's what you're going to rely on to get a PhD, you're going to be a graduate student for like 50 years because you're never going to be motivated enough to put in the work. You know what I mean? For a person that works at a school, I spend an awful lot of time telling people not to do any more school. Right now, I'm telling you, don't do a PhD. And the only people that should be like, oh, whatever, are the ones that know right away that they have to get a PhD. Because if I ask you, what are you going to study for your PhD? You're going to know. You know, I read about this, and I think I need to know more about that. I need to know more about that. Not for some stupid career, not to satisfy some parental fulfillment as they try to live their lives through you, but because you personally, and only you, have to know. Then you might make it. You know what I mean? I even try to talk you out of the bachelor's degree. Well, people with bachelor's degree make more money over the course of their lifetime. They also start off at negative $250,000 and at least 4 years behind. Negative $250,000 and 4 years behind. So are you going to make that up? As you sit there getting crushed under debt, which is legally impossible to discharge. This is why everybody wants to get you into student debt, because you can't get rid of it. You start a business, business goes into debt, business fails, declare bankruptcy, and it's over. Student debt follows you forever. You know what I mean? I guess it's a really weird thing to hear college professors say that for the most part, these days, college is a scam. That's it. It's a scam to get you into debt, undischargeable debt, that they could just sell to someone else. So so the person that's offering you the debt is not even worried about whether you're ever going to repay it. You know what I mean? It almost seems criminal, like a scam, but here we are. What are we talking about? Oh, yes, the vector field. You got to learn to read the signs about school. Like if you're at a company and you said, boss, why am I not getting any promotions? They're like, well, you need a master's degree. It's like, oh, well, if I get a master's degree, will I get the promotion? The boss is like, oh, sure. And you'd be like, oh, are you going to pay for this master's degree? If they're like, oh, no, that is your cue to start looking for another job. It's like, ah, thanks, boss, I understand. And your boss will be like, well, are you going to resign now or going to stay here and look for another while you're looking for another job? So I'm going to take the second one. I'm going to stay here, but I'm looking for another job. Now, if you're at a company and it's like, well, too advanced, you're going to need a master's degree. You're going, well, are you going to pay for that? If the company's like, oh, yes, of course. Are you crazy? Then yes. Get the master's degree because that company cares about, or they don't care about you. Let's be real. They don't care about you, but they want to keep you around. It might be because they look at the cost of your labor and how much value it produces. Then they look at the cost of educating you to to another degree, and said we can afford that and still be making money off this person. You know what I mean? I worry because some people are like, oh, I just want to go out there and make what I'm worth. That is literally not possible. That could not possibly ever happen. You can't be employed by someone and make what you're worth. Because if I'm your employer, my business works by getting more value from your labor than I give back to you. If your labor is worth $100,000 a year, I am absolutely not going to be paying that. How am I going to make money? You get $50,000. I get that $50,000. I apply that to everybody in the company. And if y'all work really hard, I'll be able to buy another boat. You know what I mean? What are we talking about? See, the reason I worry about this is that I have a feeling that all high schoolers are being lied to. It's like, oh, you've got to go to college. If you want to make things happen, if you want to, I don't know,
Yeah.
whatever they dangle in front of you. Usually for high school students, if you want to make money, how about that? Make money. Independent. Are your parents oppressive? You want to escape them? The way is money. Get a college degree. Come on. You'll make some money. You can get away. Or if your parents are supportive, it's like, oh, your parents are supportive. Well, don't you want to make them proud by getting your college degree? See, it works no matter what you walk in with. Anyway. The big idea that we want to get across here with this divergence of a vector field, think about source points and sink points. The divergence, we're going to have to think about this. Why does this quantity, what is that telling us about the amount of boom or the amount of move at a point? But the idea with the fundamental theorem of calculus, going back to the divergence theorem and the fundamental theorem of calculus, at each point there's an amount of source or sink. And we can measure all that's going on just by looking at the vector field flowing through the surface of the solid. All right, that's going to do it for today. Think about the boom and the reverse boom in terms of divergence. I'll see you all on tomorrow.